Hello everyone, I'm Yunyang Xie. Today I'm gonna to share this journal paper. Tinkertoy build your own IoT device is. It's published on 2022 on IEEE Translations on Computer Audit Edit Design of Integrated Circuits and Systems. Its rank is Q2 in 2022. The imperfectors is 2.9. About the abstract, it can be separated to four parts. 1. IoT device limitations. IoT devices limited in structure to run common operating systems like Windows or Linux. 2. Diverse demands. These devices used in applications from smart homes to autonomous vehicles require increasingly diverse software architectures. 3. Operating system evolution. Special purpose operating systems like TinyOS, Contiki, FreeRTOS, and Zephyr have been developed to meet these needs. 4. Tinkertoy solution. Tinkertoy offers a modular approach to build customized operating systems for IoT, which are efficient in memory usage without sacrificing performance. In architecture overview, it has been separated to three parts: target device, overview of module interactions, and overview of module decomposition. Tinkertoy is composed by these 10 modules: constraints, scheduler, memory allocator, context switcher, execution state, system call, dispatcher, kernel service routine, execution models, and task control blocks. When the system boots, the kernel initializes itself and lets the watchdog text run. 1. The watchdog text invokes a system call to wait until the worker's task finishes. 2. The system call resists an exception, causing the processor to switch to privilege mode and jump to a predefined kernel entry point in the context switcher. 3. The context switcher preserves the machine execution state on the watchdog's task stack and restores the kernel state from the kernel state. 4. After when it returns to the dispatcher relies on two companion to process the request. 5. It calls the services identifier finder to retrieve a unique service identifier. 6. That is subsequently needed by the service routine mapper to select the kernel service routine. 7. That implements the system call wait. The routine receives as a reference to the watchdog task. 8. And finds that the task should be blocked, so it asks the scheduler to execute the worker task. 9. Which is then returned to the dispatcher. 10. The dispatcher knows the next task to run, so it asks the context switcher to exit from the kernel switch back to the unprivileged mode. 11. And resume the worker task. 12. Also not used in this example. There are multiple memory allocators that provide dynamically allocated memory for the kernel and use applications as needed. This chart shows the relationship between a customized kernel, modules, components, and building blocks. So in the scheduler part, they have separate two parts: module decomposition and building customer schedulers. In module decomposition, a scheduler maintains one or more queues to keep track for ready queue tasks and decides which task to run in response to external events, such as a new task arriving in the system. 1. Policy component. The policy component manages the ready queue, reflecting whether a scheduler is prioritized. It is exposed to primitive ready and next to enqueue and dequeue a task, respectively. The queue accepts tasks only if they are schedulable, so we define the classes schedulable from which your schedulable task must inherit. 2. Event handler component. The event handler component reacts to scheduling events that can occur on a system and reflects characteristics such as whether a scheduler is preemptive. For example, when a new task is created, a cooperative scheduler might keep the current task running, while a preemptive one might run the task with a higher priority. These two different reactions are reflected in the implementation of the task creation handler. About the building customized schedulers. Tinkertoy provides a builder class to assemble a scheduler from a policy component and a collection of event handlers. We illustrate this process assemble a simple F5 scheduler. 1. System requires let us say that we want to build a scheduler for a kernel that allows a process to create another process. Green queues the processor voluntarily and wait for the process to finish. We assume the extensions for a user process that never terminates. The kernel expects all processes to run in a rival time order and wants to track the number of times a task is preempted. The system doesn't have a hardware time. 2. Assembling schedulers. The above requirements suggest that we need 5 event handlers. 1. Creation. 2. Termination. 3. Yield. 4. Block. And 5. Unblock. Since the system has a never terminating user process, there is always a runnable process, so we don't need an idle task. We build a new policy component on top of FIFO late increment the preemption counter of the test to be included. In this evaluation, they have given an example about automatic wet watering system. If we want to make an automatic watering system for party plants, it includes 3 devices: a monitor, an actuator, and a gateway. Each needs a custom kernel. We use the monitor checks soil moisture with a sensor and signals the actuator to water the plant if dry and stop if wet. The actuator attached to a water bottle opens or closes the gate based on alerts. Optionally, a gravity sensor in the bottle can alert user or lower water via coax ports to the Linux server through the gateway, which translates between coax and HTTP messages. Authors assess the implementation effort of each device kernel using the source line of the code SLOC, and each kernel's deployment is tailored to specific device requirements, which share the components and distinct modifications for individual functionalities. 1. Monitor kernel requires an event-driven kernel, handling timer, dry, and wet layer events. The kernel schedules these events. With soil events have higher priority. System deployment includes a preemptive scheduler, UART, sysdig, and sensor drivers. The event control block and system calls are optimized, needing only 65 SLOC. 2. The actuator kernel. Similar to the monitor, it handles UARTRX, interrupts, and message water gate operations. It uses a cooperative scheduler. The kernel is largely similar to the monitors, but its addition no system code for gate control. Total 90 SLOC with some shared and modified lines from the monitor kernel. 3. Gateway kernel. Designed for concurrent handling a coax HTTP server message. It requires a thread-based model and a cooperative scheduler. It includes a memory allocator for thread 6 and a modified UART handler. The kernel is optimized for continuous operation without thread termination, totally 122 SLOC. This has 3 parts in compression resource. 1. Application porting. 3 RTOS and variable thread-based system. Handling porting differently. 3 RTOS use event group for event-driven programming, while Zephyr use binary server first. In 3 RTOS system, calls are like library calls with no context switch, whereas Zephyr can perform context switches if configured for a user space, which we disable for fairness. 2. Flash and memory footprint. Tinkertoy has a smaller footprint than FreeRTOS and Zephyr due to its efficient test control block and selective inclusions in kernel data structures. Zephyr reserves additional space from kernel configuration and memory management routines. 3. Active stack usage. Tinkertoy shows lower kernel and user stack footprints compared to the other systems, especially in event-driven setup. The different networks in thread-based systems like the summary rarely also get. The assembled kernel provides the extract functionalities needed by particular applications. So Tinkertoy-based kernel have 1.5 times to 4.7 times smaller memory footprints than the other popular IoT operating systems, and comparable performance to them. However, there is still a large room for future improvement, such as standard API packages to improve applications portability, source-to-source compilers to translate thread-based programs to event-driven ones, and vice versa. After this research, authors have made these three conclusions. 1. Efficient customizations. Tinkertoy allows the assembly of customized operating systems for specific applications using fewer than 150 lines of code, offering configurable and composable components. 2. Optimized performance. This system precisely meets application needs, significantly reducing memory usage by up to 4 times compared to existing IoT device systems, without compromising performance. 3. Flexibility for device applications. Tinkertoy exemplifies a method that achieves the necessary flexibility and configurability to satisfy the requirements of the heterogeneous applications. And thanks for your listening.